All right, hey everybody. So last time we talked about right triangles. More specifically, we just kind of talked about the Pythagorean theorem and how to use the Pythagorean theorem to essentially classify what type of triangles we have. Okay, so one of the what we're going to be looking at today is special right triangles. So right triangles that kind of have a unique feature, so to speak, or rather, they're very like I guess what's the word I'm looking for? Very similar in nature. Instead, so that we have 45, 45, 90, which is going to be kind of unique in the way that we are be able to, once we understand parts of it, right, we can kind of actually solve the entire triangle. So 45, 45, 90 is also called a right isosceles triangle. Okay, and so kind of what this means, if it's right isosceles, again, since my longest side, the side opposite 90 degrees, my hypotenuse, it's right. The only possible ones that can be congruent in order to make this isosceles are the two legs. Okay. Now, why it's called 45, 45, 90? Because if I think about this, and if I think about this angle right here, okay, so recall that that symbol actually is the symbol used as a variable for an angle. If I think about an isosceles triangle, right, that means the isosceles triangle theorem tells me that these two have to be congruent. Okay, so since they're congruent, right, if this is theta, okay, and that means that, hey, if the 90-degree angle's in there, what's left for there to be for these two angles? Well, only 90 degrees, because the triangle adds up to be 180, right? The interior angle summed. So if they add up to be 100, or if these two add up to be 90, and they're both the exact same angle, right, that must mean, right, that both of these guys have to be 45 degrees. Okay? And so that's why it's called 45, 45, 90. So now when we're kind of looking at the sides, we want to kind of see what happens here. So let's just say hypothetically I have this leg here. And let's just say that it has a length of x. Well, if this is a 45, 45, 90 triangle, it's isosceles. That means that if the side length on the left is x, that means the bottom has also got to be x. Okay? And so now what we're going to do is we're going to solve for what the hypotenuse has got to be. Okay? So let's just call this my hypotenuse. All right, so just for the sake of things, let's just call it HYP. Right? Okay. So using a Pythagorean theorem, which we talked about last time, all right, we know that if we take x squared and we add it to x squared, so the sum of the lengths or sum of the squares of the two legs, right, that's got to equal whatever my hypotenuse is, right, squared. Okay. Well, if that's the case, just kind of using normal algebra or simple algebra, I've got x squared plus x squared. Well, that's 2x squared is equal to my hypotenuse squared. Now, in order to solve for what this side is, right, what I've got to do is I've got to take the square root of both sides, right, in order to solve for my hypotenuse. Right, and I'm left with, well, that's square root of 2x squared is equal to my hypotenuse. Now, x squared is a perfect square, so I can actually bring that out of the radical, and I'm left with x rad 2 is my hypotenuse. Okay, so that means that if this side is x, this bottom side is x, that means that this side is x rad 2. Okay, I'll actually erase this. And so you can see, and so I'm actually able to tell a lot about these triangles just by giving one side. And we'll look at some examples in just a moment. Okay. So now I want to look at a 30, 60, 90 triangle. So it's this other special type. Okay. And why it's called a 30, 60, 90? Well, of course, because since this is obviously my smallest side, so let's just say that this one's 30 degrees, and this is my 60 degrees. Okay. Again, if one of the angles is 30, the other one has to be 60 because that 90, it leaves us with only 90 extra degrees to kind of work with. Also remember, in right triangles, the two acute angles are always complementary. Okay, so and so we're going to use y in this case instead of x just to not get confused with the two triangles. So that's it as far as the angles are concerned. But now let's kind of look at, well, what happens if this has a length of y? What are my other two dimensions going to be? Now that's where it's going to get a little bit tricky. Okay, so what I'm going to do in order to solve this and figure this out is I'm going to go ahead and I'm basically going to reflect this guy, okay, about itself. So this is still 30 degrees, this is still 60, and now I've got a 60 degrees over here and a 30 degrees over here. So all I did was basically reflect it across itself. Well, if these two are 30 up here, that means that this top part's 60, and so eventually what I've just created is a right, or it's not a right triangle, is an equilateral triangle, where all of my side lengths are congruent, okay? So kind of going back, if this length is y, right, I know that this length is also y because I reflected it, which means that the whole length of one whole side of this equilateral triangle is 2y, okay? Well, if this whole length is 2y, that means that this whole length is also 2y, which means that my hypotenuse, this length right here, has got to be 2y. Now the last thing that we want to figure out is what about this tall one? Well, kind of going, let's just call this my leg. Okay, that's the leg that we're trying to find. All right, again, applying the Pythagorean theorem, we know that my leg squared plus y squared has got to equal 2y squared, since 2y is my hypotenuse for this case. Okay, so I still have leg squared plus y squared is equal, now when I square the 2y, this becomes 4y squared. I'm going to subtract y squared from both sides, and I get my leg squared is equal to 3y squared. Take the square root, take the square root. I'm left with my leg has got to equal square root of 3y squared, which, right, y squared is a perfect square, which is equal to y rad 3. Okay, so my leg here is actually equal to y rad 3. So kind of applying that to our triangle up here, right, that means if I know that this side length is y, I know the hypotenuse is going to be double whatever it is, and then this piece right here is going to be take whatever y is and multiply it by a factor of rad 3. Okay, and so that's kind of the idea for how our 30, 60, 90 triangles work. Okay, so let's look at some examples of how we can apply this. Okay, and again, when I do this, right, I'm going to look at some examples, but what I'm going to do in the top left-hand or right-hand corner is I'm actually going to recreate kind of my triangles here. I'm going to say, well, you know what, I've got my 45, and again, I'm just kind of doing this sloppily. We got, let's just say a 45, 45, 90 triangle. Okay. Again, how that kind of worked is if I have this side length as x, this side length is going to be x, and this side length is going to be x rad 2. If I look at my 30, 60, 90 triangle, right? Obviously my smallest side is 30, my other one is 60. So if this the smallest side is y, the hypotenuse is 2y, and then the other leg is y rad 3. Okay. So how this applies and how we're going to use these, right, is in, for example, number 1. We want to find the missing side lengths, okay, and then leave our answers in simplest radical form. Well, number 1 is a 45, 45, 90 triangle, and the reason why is because if this angle right here is 45, that means that this one has to be 45, okay? Which means that these two sides are congruent, which means that V, right, is going to equal the same thing as the other leg. So in this case, V is equal to 5 rad 2. Now, since X essentially, or V is 5 rad 2, I know that in order to get the hypotenuse, U, right, I know U is going to equal whatever V was times rad 2. Well, V was 5 rad 2, so U is equal to 5 rad 2 times rad 2, which is equal to 5 times 2, which is equal to 10. Okay? So what that means is that for this side length is 5 rad 2, and this side length is 10. Okay? And that's how we apply 45, 45, or apply with 45, 45, 90 triangles. We'll do it again here with this example number 2. Okay? Okay, we want to find y and x in this case, right? Since this is 45, sorry, I used green for that. Since this is 45, this must also be 45. Now, since this is 4 rad 2, that means this side has got to be 4 rad 2, which means y is equal to 4 rad 2. Now, x, right, this case is supposed to be whatever my leg is multiplied by rad 2. So in this case, since y is my leg, x is going to equal to y times rad 2. Y is 4 rad 2, and then it's times rad 2, which is equal to 4 times 2, which is equal to 8. Sorry, x is equal to 8, not y. So in this case, this side length would be 8 right here. And it's going to work very similarly for 30, 60, 90s. Okay. So again, if this angle is 30 degrees, then this angle is going to be 60 degrees. Okay. And now kind of applying our 30, 60, 90 rules. My smallest side is, this case is B, right? And then this one has got to be equal to double whatever B is. Okay, again, we know B is my smallest side because it's the side that's opposite my 30 degrees or my smallest angle. So I know in order to get B, I know that 2B is equal to 6 rad 3. Divide by 2, I divide by 2, and I get B is equal to 3 rad 3. Okay? Now in order to get A, right, A is going to be equal to whatever B is, because B is my smallest side, times rad 3. So this is going to be A is equal to B times rad 3. A is equal to 3 rad 3 times rad 3, which is equal to 3 times 3, which is equal to 9. So in this case, A is equal to 9. Likewise for this one, so we know that this one, the last one is rad 3, or so my side length is rad 3. And so I know that V times rad 3 has got to give me this side right here, which is rad 3. So V times rad 3 equals rad 3, divide by rad 3, divide by rad 3, I get V is equal to 1. So this side length is going to be 1. So if this side length is 1, this one's rad 3, U has got to be 2 times V, right? Which is equal to 2 times 1, which is equal to 2. So again, see how this works? The way that these special right triangles works is that the ratio between those sides is always the same. Meaning that if my smallest side is, let's just say y, then in order to get for the 30, 60, 90, right, then for the next largest side, all I do is I take that smallest side and multiply it by rad 3. And then in order to get the hypotenuse, all I do is take my smallest side and double it. Okay? 45, 45, 90s, right, all I do is I take, or these two sides have got to be the same. So if this is like 5, then this one would have to be 5. And then I would just take this and multiply by rad 2 to get me my hypotenuse. So it would be 5 rad 2. That's kind of neat. So now we're going to look at 3 different examples here, which are going to just kind of use both ideas of triangles in here. Okay, so here we have a 45, 45, 90 triangle, and then here we have a 45, 45, 90 triangle. Okay, so in order to find this, I know that this is 9 rad 7, and my whole goal is to find this side of x. Well, just kind of let's figure out, since this is 45, I know that this is x rad 2, just kind of completing what we know. And if this is x rad 2, that means that this is x rad 2. Okay? And I know that this is, x rad 2 times rad 2. Okay? So I know that 9 rad 7 is equal to x times rad 2 times rad 2, which is equal to, so 9 rad 7 is equal to x times 2, right? Which is just equal to, so then which is equal to 2x. So 9 rad 7 is equal to 2x. Divide by 2, and I get x is equal to 9 rad 7 over 2. Okay, which means that this is 9 rad 7 over 2. This is 9 rad 7 over 2. This is actually 9 rad 14 over 2, and this is also going to be 9 rad 14 over 2 for this next side. Okay. For number 6, okay, kind of the same idea. Actually, I'm going to go ahead and let you guys try to solve these last two using both ideas. So in number 6, we have two 30, 60, 90 triangles. In number 7, we have one of each. I want you to try and apply those, and then I will be posting the solutions as well. Okay, but good luck on the assignment today, guys, and just make sure that you guys, if you have any questions, please feel free to ask.